that you're here. Let's continue our discussion on the quantum features of the lambda positive universe. A brief recap. We discussed some motivation, why cosmology, why quantum, and why lambda positive as a bit of a sort of universal piece of cosmology. We discussed it in the context of effective field theory motivation, lambda being the most relevant term allowed by the symmetries of the problem, and the gauge symmetries or gauge redundancies. We discussed the geometry and symmetries of this exponentially expanding world. Recall that the expanding patch was this object over here, over L squared, where lambda was 3 over L squared. This rather large maximal isometry group, 10 generators, SO4, 1. We discussed some of the aspects in a simplified version, SO2, 1, of the representation theory of SO, 1, the unitary irreducible representations that helped us partition the field theoretic Hilbert. And I emphasized a little bit haphazardly, but let me re-emphasize it now, that these symmetries over here appear in at least 3 different ways. They are the Lorentz group of a 5-dimensional Minkowski world, they're the isometry groups of a 4-dimensional de Sitter world, and they're the Euclidean conformal transformations of a 3-dimensional flat world. In other words, these group is associated with a conformal killing vectors. It's generated by the conformal killing vectors that map a flat 3-dimensional metric to itself up to an overall conformal factor. Yeah? In other words, these are the symmetries of the 3D Ising model at its critical point if you're more of a CFT type person. Okay? So these conformal maps manifest themselves geometrically when you push the action of the symmetries to a very late time surface where the killing vectors recast themselves as conformal killing vectors of the spatial slice at scribe plus. And people have tried to exploit that structure. People have tried to exploit that structure in the hope that the methods that we have in conformal field theory might guide us in structuring observables at late times in these type of spacetimes. But I emphasize that there's some important differences compared to the standard structures of conformal field theory we're familiar with. We have an operator algebra that's generally built out of non-commuting operators living on this spatial slice over here. These operators, when acting at points on R3, do not create normalizable states. There's no analog of the state operator correspondence that people sometimes imagine in Euclidean CFT. Nonetheless, the Ward identities of quantum correlations are governed by this conformal symmetry, and this manifests itself in a variety of ways. So if you're in the mood of building some kind of conformal field theory that captures the physics of de Sitter space, you should certainly encode all of these additional features, which are non-standard, including the non-standard from the standard Euclidean point of view representation theory, like the fact that you can have, well, for SO4, 1, principal series irreducible representations and discrete series, which are not the canonical representations we consider in CFT, okay? That is a task that people are interested in, and I just want to emphasize the ingredients you would need to proceed with that. Now, that was the discussion of QFT, and in QFT we had a rigid background. There was no back reaction, no gravitational fluctuations, and we had a field moving around in this rigid background, governed by the symmetries, and there were many, many states. Most of the states break the de Sitter isometries, but there was at least one quantum state that preserved it. That's called Often it's called the Bunch-Davies state or the Euclidean vacuum or many other names. It was discovered concurrently by many different people studying quantum field theory in curved space in its early days. But the important point to emphasize is that there's a non-trivial field theoretic Hilbert space that transforms under this global symmetry group in the case of quantum field theory in a fixed background. However, when we activate gravity, the story metamorphoses into something else because we have to remember that the de Sitter isometries are a subset of the space of all diffeomorphisms, and in a theory of gravity, diffeomorphisms are gauge transformations. Their redundancies and states ought to be annihilated. But there's a more general story to be told, which is what are the constraints of a theory of gravity, and how do we systematize that idea, because this is a very perturbative picture. The de Sitter isometries assume that you are near the pure de Sitter solution, but in gravity, remember, that's just one of many solutions. There's no such thing as the de Sitter symmetries in a theory of gravity, right? That's the symmetries of a solution, not the symmetries of a theory. And always be cautious to distinguish these two concepts, yeah? Many spacetimes have an isometry, but that doesn't mean that that's a symmetry of the theory, yeah? And in gravity, that's particularly subtle, because most solutions break the isometries. So these are properties of solutions, not the theory. In fact, in gravity, it's quite delicate to define symmetries, and the best concept that people have is something known as the asymptotic symmetry group, which is a way to define a large class of solutions that have similar behavior in some asymptotia and see what transformation leave that behavior unchanged. Now, in the case where your Cauchy surface is compact or closed, the notion of an asymptotic symmetry group is very tricky because there is no asymptotia, and so there is no natural place where you can house the generators or conserve charges associated with symmetries. And so all symmetries are effectively turned off because there's no charges that we can define in any boundary in the first place. Yeah? So that's the subtlety here. And that's what distinguishes, in a very significant way, the physics of something like anti-de Sitter space or Minkowski space, where you can host symmetries at the boundary, spatial boundary or null infinity, versus this kind of a closed world. Okay, that's just a side remark, but it does encourage us to think about how to formulate the constraints of the diffeomorphism group properly, and that's done in the canonical formalism. We break the metric in this ADM decomposition that leads us via the identification of certain quote-unquote Lagrange multipliers into a constraint that has to do with spatial diffeomorphisms, that physics should be independent of our choice of coordinate system on the Cauchy slice when we want one point to another. That's part of the constraints of gravity. Nothing should depend on how we label points on the manifold. And the other one is how we embed this spatial slice in its ambient environment, and that's the Hamiltonian constraint. Yeah? So the Hamiltonian constraint classically takes the following equation, where kappa is related to 1/g Newton. We have this equation over here. And I emphasize that this equation has two features that separate it from the standard constraints of a gauge theory. Namely, it's quadratic in the canonical momenta of the field. Secondly, the quote-unquote kinetic term is not positive definite, yeah? Because this metric on the space of metrics, which is sometimes the notation people use is the superspace. The space of all metrics is a space known as superspace that has nothing to do with supersymmetry, but it is a superspace. And it has negative directions. In particular, you can codify the negative direction to be that deformation of the space of three metrics that has to do with its overall size. For instance, you could codify it as the determinant of the induced metric. Remember, HIJ is the induced metric on a spatial slice. And the negative direction of this equation is the overall scale, something that you could codify it as root h, yeah? And just to tie to an equation that we saw in the first lecture, which is the FRW equation. So now I can add some further content to what I was saying, which is that, remember we had this FRW equation where we chose a particular class of metric configurations, yeah, which had the following structure, where this, well, more generally, this is a isotropic and homogeneous space of curvature K, not to be confused with kappa. And we have this equation over here equal to 0. That's one of the FRW equations. And what's going on over here? Well, now we can compare this equation to the general equation, and we can note a few things. A was the overall scale of the spatial metric, yeah? And I noted that its kinetic term, in other words, A dot over A squared, came with a minus sign. That minus sign is precisely the negative direction in this metric, in the space of metrics over here, yeah? This is a simple manifestation of this general principle, okay? And the pi's, in this very, very minute slice in the space of all metrics, just pi is the kinetic term, the canonical conjugate momentum, just becomes A dot over A. The time dependence, the time derivative of how the scale grows with time, yeah? Kinetic, naturally kinetic term of the metric. And here we have two terms, yeah? We have a plus lambda term, yes? But lambda is the energy density, okay? So this was this plus term over here, okay? And we have a minus r, which is the Ricci scalar of the induced metric. But for these special cases, the Ricci scalar roughly scales like 1 over the size squared, yeah, with a minus sign for positive curvature, which is indeed this sign over here, yeah? So next time you see the FRW equation, you should remember this is nothing other than an expression of the fact that gravitational energy is 0, okay? And it's true not just in the pure gravity theory, but for all these more general rows that we had, yeah? So, in a sense, this negative direction in the Hamiltonian constraint is what allows us to have non-trivial cosmology, yeah? It's ironic that the existence of cosmological solutions in GR has to do with the fact that GR has to have a vanishing energy for all configurations. Because what is happening is that this is counteracting this energetic terms over here, and thus breathing kinetic energy into the metric and making it come to life in a cosmological way, yeah. You can multiply the whole equation by minus, but then you'd be making your energies negative. And so my conventions are that this is positive energy over here, and typically energy is kinetic plus potential. So this is the point I'm trying to make. So if I organize the equation to have positive energy, so if there were matter fields here, I would have the 0, 0 component of the stress tensor to have it positive energy, and I know what that means for matter because that's bounded, yeah? Then the only way this equation makes sense is to have this negative kinetic energy in the metric. So that's an interesting feature of gravity, and it's very special to gravity. And so when we think of gravity as a gauge theory, we ought to remember that there are these distinctive features, okay? I hope that's clear. Cosmology exists because energy is 0. Very exciting. And so what I want to do, right, so then what we did was we proceeded to say, well, if this is a classical equation, maybe, and this was the original work of Bryce DeWitt, which is a paper that you must read, and Wheeler was associated with the idea, and it's come to be known as the Wheeler-DeWitt proposition, or hypothesis, or idea, which is that perhaps, at least in this very semi-classical regime, where we have very gentle variations of the metric, both spatially and time-dependently, where we're not in a high curvature regime, where we're not pushing the theory to its limits, we can understand this classical equation as the limit of some quantum equation. Now, we don't know what the full quantum equation is, because that would be equivalent to the question of what is the quantum gravity. But under the assumption that there exists such an equation, if you would like the limit of that theory to give the kind of classical physics that we see in our own world, this is compatible with experiment, then perhaps this equation should be understood as a quantum equation in a particular regime. Yeah? And this is the Wheeler-DeWitt quantum equation, where these are now interpreted as operators, yeah? Operator-valued quantities. And this is an equation to be understood as acting on wave functions. Yeah? So we have, well, this equation over here, and also the more simple one to understand, which is that states should be coordinate invariant under spatial transformations. And so the postulate is that there exists in the Hilbert space of effective field theories of gravity coupled to matter, yeah, there exists functionals of matter fields and metric field configurations, yeah, that satisfy these equations, okay? And that these code, at least in this regime, quantum phenomena of the world, including quantum phenomena of the gravitational field. And note that though the equation is in an approximately classical regime, it is not assuming that H is a small linear perturbation. So it's a nonlinear equation, yeah? And so it's still a rich problem in that you could ask things about this equation. For instance, what is the wave function, if we view this as, interpret this as a wave function, for the spatial slice to be highly curved, yeah, very wobbly sphere, as opposed to a very round sphere, yeah? So these are questions that we can ask, and we don't need to ask them in a perturbative sense, if we had sufficient power to solve this equation, which is the big technical challenge, yeah? A conceptual challenge associated to this equation is that to really call this a Hilbert space, I have to also provide you with an inner product structure. And here lies an important question, which is that because of this negative direction over here, this is a little like asking the question of whether there's an inner product for the Klein-Gordon quantum particle. In other words, imagine you have a quantum mechanics of the following type, and you ask, does such a system, yeah, have a positive definite norm? Now, the indefinite sign, and this is a nice exercise for you to do, of the Klein-Gordon operator, if you perhaps remember, often this is early days of QFT courses, we are taught that that's not the right way to proceed, that what we should view this as a second quantization, and then we'd let go of the standard single particle Schrodinger picture. But here we're in a similar situation, that if we are to interpret this as a Schrodinger equation for gravity, at least in this regime, we have to confront the fact that we have this indefinite signature. So there's no canonical, as far as I know at least, canonically accepted resolution of this, but there is a regime where you can obtain some clarity about this, which is the large volume regime, yeah? And in the large volume regime, something remarkable happens, although it's extraordinarily hard to solve this equation in general, in the large volume regime, because there's some universal dominance of this equation. For instance, at large volume, this over here is suppressed. Yeah, if you have a large volume, your curvature is generally suppressed, like 1 over the size squared. Lambda persists. It doesn't dilute. It persists. Yeah? And now you have an equation that simplifies rather dramatically. And I'll spare you the details for the sake of time, but it's a nice exercise, and I gave you a reference where this is worked out previously. I can write it down again. It's one of many references, but it's good to have. So 2 references for wave functions. for the curious and the eager to calculate, you have the following references. Now, what happens in this regime is that you have two terms which oscillate very, very rapidly. Yeah? So there's a highly oscillatory behavior in the wave function. This is characteristic of WKB type behavior, but we should view that analogy with caution. But we have these two quantities over here that grow rapidly and don't code, but they don't code any non-local correlations. These are local terms in terms of the metric. They're pointwise integrals of the field, and therefore they code no non-local correlations. But then you have a term over here that can be non-local, that codes non-local correlations of the metric field, and all of this equation in this regime to leading order up to volume suppressed terms enforces that this is a functional that's not only invariant under spatial coordinate transformations along sigma, but also local Weil transformations along sigma. In other words, it's a functional that's insensitive to the overall scale of the induced metric along the surface. Now, this is interesting because that means that the overall scale is only affecting the local terms. And sort of most of the non-local quantum information of this state, if we are to interpret it as a state, is insensitive to that. And this gives us perhaps a nice suggestion for an inner product, because now if we were to think about something like the norm of the wave function or an inner product, we could imagine some type of inner product where, well, let's consider a very naive inner product that has the virtue of being positive. Maybe we should just consider the absolute value of psi squared. Now, what's the problem with this? If I just path integrate over all metric field configurations of psi, since psi is independent of the overall scale, this will immediately give an infinity that has to do with the volume of the Weil group, of the Weil transformations, right? Because you're integrating over infinite copies of the same function, and this is something that would just give a naive infinity. Now, often is the case that if we have such infinities, it's a wise idea to try to consider a slice in the space of all Weil orbits, like we do in gauge theory, and we should take a slice. So we should consider a gauge-fixed, in other words, version of the wave function, where this is a function of some slice in the space of all possible Weil transformations. Or alternatively, we should consider this to be divided by the volume of the Weil group. Now, what could this mean if such a norm makes sense? Well, we ought to remember that this equation over here is a timeless equation. Typically, a Schrodinger equation, you have h psi equals id by dt psi. But here, there's no time dependence, you see? So all time evolution, if you take this equation seriously, is trivial, yeah? E to the iht, if h is equivalent to 0, is just 1, so there's no time evolution. But when we compute probabilities or norms in a quantum system, we do so on a constant time slice, yeah? We don't integrate over all times, yeah? We say, here's my quantum state at a given time, and I'll integrate over all the possible configurations at that time to extract some expectation value. Now, in the absence of time, this is a bit strange because maybe we should just integrate everything. However, we saw that integrating over everything gives an infinity. But perhaps the lesson is that we should view part of the space of all three metrics, a portion of it to be our effective time, and probability should be computed on some constant time slice. And the natural candidate for what that time might be is precisely those directions that are negative over here. Yeah? And so one type of proposal for a norm could be that we should consider this slice in the space of all scale factors and view scale factor, fixing the scale factor along sigma to be a definition of a constant time slice. Yeah? So that's how one might be able to get time out of a timeless equation and be able to define some notion of probability. Now, this is crucial to clean up properly and understand, because when we do cosmology and inflation and things like that, we may be studying a perturbative problem, but we should hope that that perturbative problem is a perturbative limit of some nonlinear problem, of some nonlinear quantum problem. And so if the quantum problem has these features over here, and we'd like to calculate the expectation value of fluctuations of a metric field or whatnot, we may wish to derive our perturbative results, our perturbative calculations, from a framework that is nonlinear at least. Okay? And we may wish to ensure that the norm that we use in perturbation theory has properties that make sense in this framework as well, or show that they're incompatible somehow. So that would be a very hands-on connection of these more general considerations with the methodology that we use when we study fluctuations in inflation, okay? For those of you that want to connect the two pictures. Okay, now. Yeah.
This term of Down equations is K is the K curvature of the metric, yes?
K over here is curvature. This kappa is related to 1 over G Newton.
And the wave function not depends of the K curvature?
Yeah, sorry. These alpha and beta, let me give you the more complete formula. This alpha and beta are, well, I give you the precise quantities, are equal to 1 over 4G root lambda over 3 and 1 over 16 pi G root 3 over lambda. Yeah.
Yeah, okay. Because another question is, one can is needed to define the curvature of K to solve the wave equation?
Sorry?
Because K can be positive, negative, or 0.
Well, so this is coded in this.
No, the K curvature.
Here?
Yes, yes.
Yeah.
Yeah, and the wave function depends of this K curvature.
The wave function will depend.
The wave function, yes.
Yeah. The wave function will depend on this curvature. Indeed, it does. For instance, over here.
Yeah, okay. And one needing to define the curvature to solve the wave equation.
Is the so
because if K in the first term of the H Hamiltonian equation is 1 over K, yes? Of the
no,
K
this is kappa.
Ah, okay. Yeah.
Oh, sorry.
Okay,
Yeah, let me be more responsible.
Thank you.
Yeah. Versus.
Okay.
Yeah. Good.
Yeah, well, the rest is the same.
Ah, okay, great.
Thank you.
Yeah, and this is yeah. Okay. Okay. Are there any questions at this stage? So this was quite, conceptually puzzling. It remains so. We don't have a clear picture, but there are structures that are worth understanding. Yeah.
Can you repeat that of choosing the lambda as a time?
Lambda. The scale factor.
The scale factor.
Yeah. So the configuration space that lives on this slice over here is the space of all possible 3 metrics. Yeah. But you could partition this into a piece that is the volume and a piece that is, for instance, has unit determinant. Yeah. Where root 8 is equal to 1. Right. The part of the configuration space that is affecting the volume, yeah, contributes negatively to the kinetic energy. Now, also, as it happens in cosmology, the scale factor is a very natural field that we associate to cosmological time. Yeah, because we can keep track of cosmological time via the scale factor. Although t is a coordinate-dependent, meaningless thing, some of the scale factor is something we more directly measure by looking at the redshift of light and all of these things. So, inspired by the fact that in quantum mechanics, when we compute probabilities, we do so on a constant time slice, the question is whether we should analogously here identify in the space of all three metrics a natural field which has to do with the constant time slice and integrate over only the remaining quantities. Yeah. All right. Now, how am I doing for time? Okay.
Yes. Dio, one more question. Sorry. Here.
Ah.
So from your last comment, I sort of understood that perhaps you're calling time the determinant of Hij, since you in a broad sense. But then doesn't that wouldn't that be sort of like a Weyl transformation?
At late times.
Ah, okay.
Yeah.
Late times. Okay.
But yeah, no. But in principle, you could view it as it's the overall scale. I think it's you can view it as the overall scale. What happens at very late?
My fear is that you're dividing by the Weyl volume of.
Well, I'm dividing. So I could either gauge fix. So Weyl, in as much as this equation is concerned, the Weyl invariance is almost like a gauge invariance. So what I might want to do is view. Maybe it's more responsible to say, let me view the Weyl transformations as some sort of gauge redundancy and consider now a gauge fixing. Yeah?
And the determinant of that metric, you
yeah,
would call
so
time.
one, to do it responsibly, will have to be sure that they're capturing the Jacobian properly and so on and so forth. So this is a schematic equation precisely for that reason. Yeah. But the spirit, I wanted to express the spirit of the idea.
Okay, and I understood something that at some point I understood that you said that the negative directions of that operator G could be understood as time, but I do not see the connection between that statement.
So
and
think of the Klein-Gordon operator, right? So the negative direction typically we associate with the time-like direction, and in the Klein-Gordon inner product, if you're familiar with that, we have this kind of inner product where we consider a fixed time size. It's preserved, so you can define a conserved inner product for this equation, but it won't be positive definite because the Klein-Gordon inner product is positive for positive frequency and negative for negative frequency. Yeah.
Okay, and that idea is the same after.
So the idea, what happens here is that when you're in this very large volume regime, effectively you've conditioned on positive frequency solutions because it's associated to the time dependence being expanding. Yeah, and so that's what's happened. You've sort of entered a regime which is a little like the regime, the condition you need to get a positive norm out of the Klein-Gordon operator. Maybe that's a nice homework problem to look at the Klein-Gordon operator and the inner product of the Klein-Gordon. But that's what happens effectively. So, sorry?
In the Klein-Gordon field, you have to identify a conserved current.
Yeah.
What's the conserved current?
Yeah, there's an analogous quantity which is already in DeWitt's paper, which is this the analogous some superspace current that exists and is conserved in the same sense. Yeah. Okay. Excellent questions from excellent students. Now, any more questions? So what I want to do now is one more comment on this Wheeler-DeWitt before we move on to a more local description of physics. But let me make one more comment because this is an important part of the history of the subject, which was given this equation. There are many, a priori, there are many solutions. There's no argument that there should be one solution. Of course, if you go to lower dimensions, maybe there could be fewer solutions. And I should also mention another, I think, nice reference. that has been studying this wave function in 3 dimensions, because maybe some of you are interested in 3 dimensions, which is a paper, where do I have it? Of Mollman et al., where they study some nice properties of the wave function in 3 dimensions, and also a paper of Victor Godet that studies it. But they studied on more elaborate topology. So here I'm going to keep the topology of the spatial slice more simple. Now, all this is good, but in cosmology there's another thorn in the rose garden, which is, maybe we should call it a rose in the thorn garden. But anyways, there's another issue, which is that what do we do as entities in a cosmological world, yeah? If we take this very global picture of the quantum theory, yeah? So it's a little puzzling in the following sense, that we have an equation, a priori it has many solutions, and each solution will produce its own predictions, its own. Some universes it predicts may be very classical, some universes it predicts may be very quantum. In fact, even if I had a very classical universe out of the wave function, I could superpose it with a very quantum. You see, it's a linear equation. So there are many solutions and superpositions of states. And so what becomes of predictivity in this world? And this is in stark contrast, I should say, to the world of particle physics, where we control the initial state. Yeah? We control the particles that we shoot in, cause interactions, and measure the outgoing state. And that determines the experimental protocol and the theoretical protocol. Yeah? So that has always been the protocol of the quantum experiment. And it was always crucial that we prepared, you know, a system, a quantum system in a given state, and that we have access to such preparation. So another puzzle that is bothersome in this situation is that who prepared the state, or how do we know? How will we ever extract predictions from a state whose properties have not been prescribed to us by some theory? So this is an expression of the problem of the initial state, yeah, which is inherent to the questions of cosmology, unlike particle physics, yeah, or standard quantum problems. And this is an interesting puzzle, because if there's many solutions to this equation, maybe there's a bigger theory or a more complicated theory that somehow selects naturally a particular state or class of states, or maybe our role is to reconstruct the state, and then hopefully when we reconstruct sufficient parts of it, we can uniquely fix it and extract predictions from the state we fixed. But there's a protocol here, a quantum protocol, that changes from the one that we do in the ordinary quantum experiments. Yeah? And that's something that has to be noted. And throughout time, people have considered different solutions. And there's one solution, just to give you an example, one that played a prominent role in a lot of discussions of the quantum cosmology literature, which is that of Hartle and Hawking, okay? And so I just want to comment briefly on what goes into this state, for the sake of providing an example. Now, you may be familiar with the fact that when we have a path integral formulation of quantum mechanics, yeah, So let's go back to the basics. Path integral formulation of quantum mechanics. And this was briefly mentioned in Guy's talk yesterday, but I want to re-emphasize it in the context of gravity, which was not part of that discussion. Imagine I tasked you with the following exercise. I give you a Hamiltonian in a quantum mechanics, yeah? So some Hamiltonian, it could be as simple as the harmonic oscillator. Simple. Imagine we have just a single particle quantum mechanics, yeah? So this could be something, some potential, some momentum. And I tasked you with calculating a solution to the Schrodinger equation from the path integral. Yeah? Sorry, what? Plus p squared. I've been too influenced by the cosmology. Okay. Yeah. So, quite remarkably, and this is a nice exercise that sometimes we learn in the class and sometimes we don't, it turns out that the path integral, yeah, over configurations, so this object over here, where x at t equals 0 is some value x tilde, and then we can fix the state at some time t initial to be x0 or whatever. So this thing, which is a transition amplitude, yeah, it tells us the amplitude for a state to evolve during a time period. Time period ti or t, yeah, from some initial state to some final state. Yeah, so this is a transition amplitude. Yeah, this object over here, if I fix x naught and view this as a function of x tilde, yeah, is a solution to the Schrodinger equation. Yeah, so there's a link between the path integral formalism of quantum mechanics and the solution space of the Schrodinger equation. And it's a remarkable link. It's a non-trivial derivation. But if you recall how we construct the path integral in the first place with this schematic derivation where we discretize the space of all paths and put in a Hamiltonian and evolve, you'll see that there's a direct link between the Hamiltonian formalism and the Schrodinger picture. And in particular, this gives us access. So now if I asked you further, I want you to give me the ground state wave function of the quantum system by a path integral computation. Yeah? If I tasked you with that, you may be inspired to insert a complete set of energy eigenstates, yeah, into your path integral. Well, let me give you the output of that. Yeah, good old quantum mechanics. Sum over the energies, e to the I, e, t, I. Okay, so we have this object over here. Now this over here is nothing other than the wave function psi of x tilde, which is an eigenstate with energy E. And this over here is psi star of x naught with energy E. Yeah, so we have this sum over here. Yeah, and so now maybe it's a little more transparent. If I was tasked to identify the ground state wave function, in other words, psi of E for the lowest value of the Hamiltonian, yeah, one method that you could implement would be to add a small I epsilon, a small imaginary part to Ti that drives it at large Ti to exponentially suppress all these terms as compared to the one with the lowest energy. Yeah, so this is the I epsilon prescription that we use to drive out all of the excited states, yeah, and link and link, check the sign please, and link and have the output be purely that of the ground state itself. Yeah, so that's this I epsilon prescription. That's its role in life. And therefore, if we take this path integral over here, yeah, and now understand it in a slightly broader sense as the x of t's being paths not along the real time axis, but along the complexified time axis. Yeah, so now we have to view t as a complex parameter, yeah, that's allowed to delve into the deep imaginary past, yeah. So this requires a complexification of the space of paths that we have, and so there are assumptions that go into that being a possibility. But what we can do is, from a path integral point of view, declare that if we force the configurations to effectively vanish in the far Euclidean past, that the path integral receives no contributions from there, and push this limit to our past boundary condition, the output of the path integral as a function of x tilde has to be the ground state wave function as a function of x tilde. And so we have a path integral derivation of the ground state of our quantum system. Now, this is useful for those of us interested in vacuum states. Now, if, however, it happens that our system has no vacuum state, well, we shouldn't really call it a vacuum, but we can ask, and this was the inspiration in Hartland-Hawking and Bunch-Davies and others, you know, trying to define the closest analog to a vacuum state in the context of cosmology. And the idea was, well, maybe we should implement some smoothness condition in the imaginary past. Yeah? So this was the inspiration. So on general grounds, again, so let's consider our wave functional, which is the overlap of our field operator eigenstate with some state. By general grounds, we could imagine some path integral over the state. Well, in fact, the path integral is not just over Hij, but over the space of all four metrics. So this would be a transition amplitude, where this is the Lorentzian-Einstein action. Well, with boundary conditions where you have G equals to H, the induced metric at the given Cauchy slice final is equal to Hij, and perhaps, well, let me write it like this. Let me go through the motions. Yeah. So you enforce that on a given Cauchy surface, your path integral, your induced metric is HF, and on another Cauchy surface, your path integral is HI. Yeah, and you do this path integral, so that's a little like calculating the transition amplitude of the metric, yeah, between all possible evolutions, yeah. Of course, this already is much more subtle. This transition amplitude is much more subtle because there is no actual time evolution, and so things like cutting this and resolving the identity become rather conspicuous. However, you can certainly define this path integral formally, and the output as a function of Hij(J)F along the similar lines to the output of this being a solution to the Schrödinger equation, you could anticipate solves the Wheeler-DeWitt equation. Okay, so that is one piece of inspiration in this paper. And these things can be established to a reasonable level of rigor. And the second inspiration is, what do we mean by implementing the Euclidean condition? what do we mean by switching off the fields in the Euclidean past? And here comes the second portion of the inspiration, which has to do, and let's consider again as a toy configuration, the global de Sitter. Yeah, so this is the 3-sphere over here, and yeah, so if there were small, so remember, if we were only dealing with small fluctuations, we could certainly ask these questions, so we would have an initial deformation of the round metric. So this is the round metric on the 3-sphere. And then we could consider the path integral that evolves this thing perturbatively to sort of some deformation of the round metric of the 3-sphere at late times. And there's some, if Hij, well, so there's certainly you can certainly imagine this calculation perturbatively. Beyond perturbation theory, it's harder to do the calculation explicitly, but you could do it order by order, certainly at tree level. But the important piece of insight in the Hartle-Hawking paper was that if I take t to Euclidean time, this metric becomes the following metric, which, as I mentioned earlier, is the round metric on the 4-sphere. Yeah? So there's this remarkable fact that the infinitely expanding world in Lorentzian signature collapses onto the most closed conceivable universe in Euclidean signature. And the idea of Hartle and Hawking was that what replaces the Euclidean past is a portion of this 4-sphere that causes the space to cap, yeah? And they said, well, maybe we should require that there's no singular contributions from the path integral in this portion over here. And so they imagined that what replaces the condition of the Euclidean past over here is a smoothness condition, yeah? And they defined a path integral of the following type, which is, they said, well, inspired by this picture, let's define the gravitational ground state wave function in the following way. Let's take the path integral of all, and this is obviously a very formal expression, and I'll express in what senses it's formal. Let's compute the space of all 4 metrics, all 4 metrics on a manifold that has a topology, on a 4-manifold, which has a topology with a single boundary. We can take the boundary to be a S3 topology. We could consider more general things, higher topology, even topologies with boundaries. But let's take it to be S3 over here, and but no other boundary. So it's the capped, yeah? So that's the manifold that they imagined this path integral configuration space to be living on. And they said, now let me path integrate over all smooth metrics, and this will be now again necessarily complexified, yeah, because you can't cap off without complexifying time, but complexifying time is not meaningful in gravity. What's meaningful is the metric, and so complexifying time becomes the complexification of the metric field itself. Remember, the Euclidean continuation is a complexification of the metric field, yeah, because that's there's no coordinates are not the meaningful players in the theory, it's the metric itself. So this is in some complexified metric space where you impose a real valued condition on S3, namely that the induced metric on H3 is Hij, and you then no longer specify anything else. You just path integrate smoothly, that was their idea, over all configurations. And that was the no boundary Hartle-Hawking proposition. And one can study this wave function and see what features it has. Yeah? So this is, and their proposal was that maybe there is a distinguished solution to this equation, and the distinguished solution is precisely the one that requires no further specification in the Euclidean past. Okay? Now, There are some challenges, but let me make, so that, okay, are there any questions at this point? We've defined a formal object over here. This object is argued to constitute a solution to the Wheeler-DeWitt equation in the spirit of the path integral construction of solutions of Schrodinger equation. And it has an inspired condition over here, which is this initial state. It's a choice of state, yeah. The Euclidean continuation is a machine that allows us to select a state. It's not that the theory is living in Euclidean signature. The theory lives over here. We are living in Lorentzian signature. This is a machinery, just like it was over here. The particle isn't living in Euclidean signature. It's just a machine that selects for us a particular state. Okay? And so they made the bold claim that this may be a distinguished state of the world, of a closed world, and prompted the study of this path integral. Okay, questions?
How dependent is the prescription or the no boundary prescription on computing this state on the fact that the metric, the components of the metric is time symmetric? Because the slides that you did in the...
No. So good. Okay, I should be clear. This picture is meant to be a guiding picture. This over here is a prescription that has nothing to do with any symmetries being present in the metric. Yes, you define this manifold, at least as in principle. You define this manifold, and all metrics, the only reality condition you've imposed is what the induced metric is on this boundary, Hij, that it's real, yeah? And then you assume smoothness everywhere else. In a semi-classical regime, it may be approximated by some highly symmetric saddle, but that's a property of the solution. It's certainly not a property of the path, nor does it necessitate that. Yeah.
Here, in this sense, you define the curvature of the manifold in the sense of you have the curvature that's define the curvature of the manifold that is closed or open.
Not the curvature, the topology.
The topology, yes.
Yes,
the
so you
topology.
specify the topology. However, if you take their proposal seriously, in fact, a priori, there could be contributions that come from more exotic topologies.
Okay. Yeah.
This part of the Hartle-Hawking wave function, was a point I was going to make later, is less studied and less understood. In fact, it's not even clear that these contributions will solve the Wheeler-DeWitt equation, as a matter of fact. And but let me not go there now. Okay. But that's a very good question. Yeah.
Thank you.
It's actually it's a follow-up to his question.
Yeah.
It's very specific. Okay, no problem.
So it's just a quick question. If you are defining the boundary here
Yeah.
as an Euclidean topology, why don't you have to consider the Euclidean action?
It's a complexified, you see, Euclidean or Lorentzian is just a matter of how conventions on G. It's a complexified action. So if you want, I can view it like that, but the saddle will generally be complex.
Okay.
So the signature is immaterial, provided that it's sufficiently Euclidean in the region where you cap it off. Yeah.
Thanks.
So in this prescription, one considers a sum of contributions from different metrics and different topologies in the path integral.
In principle.
In principle, yes.
Although nobody specified, I should say, that the part with the topology is much less clear, and in fact we don't have a classification of four manifolds, so it's not even clear that it's a mathematically sensible thing to do.
And that said, in this sea of confusion, let's say,
Yeah.
usually when one quantizes the metric a la Wheeler-DeWitt,
Yeah.
to me the topology is fixed, but the metric
No.
is
Yeah,
operated.
I should distinguish
that's
two
my
things over
question.
here.
Uh-huh.
Yeah, let me be clear.
Please.
There's the topology of the boundary, and the topology of the infilling four-manifold. In Wheeler-DeWitt, what we discuss is the topology of the boundary. I'm happy to keep that fixed, but even if I do, the infilling, yes, there could be many four-manifolds that admit a slice with a three-sphere topology.
Okay, yes.
That's the real subtlety.
I see.
And Wheeler-DeWitt has nothing to say about that. Yeah. Okay.
Thanks.
Yeah. I'm going to come back to that. This topology question has been bothering me for some time. Okay. Any more questions? Okay. So, congratulations to everyone for still being alarmed and awake. Alert, sorry, not alarmed, alert. I lost my track of thought. Ah, yeah. So let me discuss some of the theoretical, technical challenges with this path integral. So I should say this path integral can be studied certainly in a saddle point approximation and perturbatively nearby. So and indeed, in the saddle point approximation, what happens is this manifold becomes a portion of the hemisphere, the four-sphere. You slice it on a three-sphere. Yeah, and you could consider making small wobbles of the metric on S3, and this will give small wobbles on the filling, and you can study perturbation theory. And the perturbative fluctuations of this wave function have indeed this nice sort of structure. So if omega is a coordinate on S3, what you have is in the spirit of the so this is a very large volume. So now let me take again the large volume where things are a little more simple to write down. It takes this form that we anticipate from the structure of the quantum field theory wave function. So it mimics, so this over here is the Gaussian. So it's a Gaussian suppressed, so small wobbles around the S3 are Gaussian suppressed. So it predicts, at least if you're near the round S3, small sort of deformations of the geometry cost probability, if we interpret this as a standard probability, psi squared. Yeah, so it's Gaussian suppressed, so that's good, nice sign. Yeah, Gaussian suppressed. So if you wanted to know whether, if you so happen to condition that your wave function is, that you're sampling the wave function near the round S3, and you wanted to know whether it's wobbling the sphere costs or enhances probability, cost probability. There's many higher non-Gaussian terms as well, h cubed and h4. These have been studied nicely at tree level. Little is known at the loop level. But it's an object that seems to have a reasonable perturbative expansion, yeah. However, one should say that in defining this object, part of the path integral lives in Euclidean signature because we have to cap the manifold, at least where it caps the definition of the capping. You see, what does it mean to cap a complex metric? It's useful that at least where we cap that the metric is real valued, so that we can specify that it looks locally like a piece of a disk. Yeah. But the real at least technical, perhaps conceptual issue is that the Euclidean action of gravity, it's a property that I think is very important to emphasize. So we are accustomed in quantum field theory, so let me make a general point, and then I'll make a point about gravity. We are very accustomed in quantum field theory to going to Euclidean signature to calculate certain physical quantities. Yeah? In fact, the axiomatic rules of quantum field theory are often formulated in Euclidean signature, and we consider analyticity properties of the space of correlation functions. And the reason for that is that we don't have to deal with these phases, these oscillatory phases. The path integral is a little better defined. It's suppressed. It's positive definite for stable quantum field theories. And so it's a very natural property of quantum field theory to go to Euclidean signature. When we study finite temperature quantum field theory, for those of you who are familiar, it's very typical to go to Euclidean signature as well. This was mentioned in Tarek's lecture a few days ago. And so you may hope that gravity in Euclidean signature has good positivity properties. But there's a little bit of a sticking point. The conformal mode problem, which I think needs to be emphasized, is often considered an irrelevant technicality, but I like to emphasize it because we cannot leave these kind of details unchecked, which is that if I consider the Einstein-Hilbert action in Euclidean signatures, in Euclidean signature, up to boundary terms, it takes the following form. Yeah. So you have the Euclidean gravity action. So what does Euclidean gravity mean? It means I have a Riemannian metric now rather than a pseudo-Riemannian metric. So a metric that locally, always at any point, its eigenvalues are plus, 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 plus. Yeah. And this is my action. And when we have objects like this, yeah, the Euclidean path integers, we generally, in quantum field theory, likes this object because we know that most field this is a positive quantity and everything costs, yeah? And so it's sort of a nice object to work with. Now, is that the case for gravity? And the answer is no. So in gravity, if I take my Euclidean metric and I consider, for instance, configurations where I excite only the conformal factor, yeah? So delta mu nu is just flat metric on R4, and I have this omega over here. What happens is that this action becomes, and this is a nice calculation, effectively the kinetic term of the conformal factor. So I'll just write it schematically to emphasize the salient feature, is the wrong sign kinetic term. Yeah? So the Euclidean action of shell as a function of general configurations is not positive, period. It has arbitrarily negative contributions. For instance, I could make omega a very rugged function that has high derivatives, and I can get more and more negative contributions, yeah, rendering this object a little bit subtle to define, because a priori, any Euclidean path integral gravity will be driven to the place where the action is negative most, such that minus SE is as positive as it can potentially be, yeah, leading to a Euclidean catastrophe. Yes? This is the conformal mode problem, and this is a peculiar fact of Euclidean gravity, which is nothing other than the Euclidean manifestation of our cosmological kinetic term in the Wheeler-DeWitt equation. Yeah? And so, just like there was a bit of a pickle in the Wheeler-DeWitt Hamiltonian constraint equation, that of course was crucial for the physics to make sense, because we need energies to vanish. This gives rise to cosmological solutions. We confirm them experimentally, and so we good with that sign. Over here, it means that if we are to do Euclidean gravity, yes, we have to confront the fact that this has to be understood in some formal sense, yes? Because the answer to this path integral, if you take it literally, is infinity, yes? So that's an important point to emphasize. And there's no first principles resolution to this. However, there is, I think, supporting evidence that this prescription, at least at the saddle point level, including loops, is a sensible prescription, thanks to the fact that in certain contexts we have an alternative definition of these kind of path integrals, namely in ADS CFD, as an example, where we know from a very, very rigorous place, or at least in physics terms, a very rigorous place, that Euclidean conformal field theory is an extraordinarily well-defined notion, yes? And if we have a Euclidean CFD, there ought to be a corresponding Euclidean gravity with ADS asymptotics that is a sensible object as well. And so by the very basic rule of ADS CFD, which remember is in Euclidean signature, yeah, it's that the Euclidean ADS partition function is equal to the Euclidean CFD partition function, including sources, yeah? But this part of the equation suffers from the conformal mode problem, yeah? And so the prescription we use, in other words, what we do is we complexify the contour of path integration in this direction so that it picks up a saddle and perturb around each saddle point contribution. That prescription has evidence, quantitative evidence to work, at least in the context of lambda negative, but it's a prescription that applies to the behavior of the conformal mode of the metric deep, deep in the interior space that isn't particularly sensitive to the fact that you're asymptotically ADS. And so one thing that ADS CFT gave some confidence to was the fact that Euclidean gravity may be, in this sense, of the saddle point plus loops, a reasonable methodology for quantum gravity in this regime, yeah? And that's important because if it's true, it's a very powerful tool. Another piece of evidence has to do with the thermodynamic properties of black holes, which we often compute using these kind of Euclidean path integrals. And sometimes we have alternative descriptions of the thermodynamic properties of black holes that we can compute to very refined levels, and we can compare the two sides again. And so the evidence in favor of the conformal mode problem comes from two sources: black holes, thermodynamic type calculations, where we have sometimes enough details to compute the Euclidean path integral, including loops, and compare to formulas that come from other methods, counting problems, and the fact that Euclidean CFT is well defined, and so there ought to be something like a Euclidean Euclidean gravity with Euclidean ADS boundary conditions. Okay, so that is my apology for Euclidean gravity, because it's we're going to pursue this method further down the line. Okay, are there any questions at this stage? And how am I doing for time? Sorry? Left. Yeah.
Dio, one question. You mentioned that it is subtle, the idea of big rotating in gravity, because the simple I tau that we do in quantum field theory is a little bit tricky, and you said that you interpreted that as moving the metric around rather than the coordinates. Would you picture like grabbing your favorite G00 and put it a phase that
For
slowly
example,
moves the
yeah.
That is the picture you have.
That's a
when you say-
complexification of the metric.
And whenever this complexification is not, let's say 0 or pi, can I draw something in the blackboard for the picture I have in my head? Because for 0, I can draw that picture, and from pi, I can draw that picture.
Maybe you can.
Okay. We can discuss this later if you want, but I'm very interested in this.
Yeah. Okay, any more questions? I'm not good at visualizing things, but it is, one ought to view it, I think, as a complexification of the metric. Yeah. And like I said, even in quantum mechanics, when we do this I epsilon, we are already flirting with the idea of complexifying field configurations. This is not something specific to gravity, and this is important to emphasize as well. Yeah. Any more questions? Yeah.
Sorry, I didn't understand if there is a resolution of this problem that you have a...
There is no first principles resolution of the conformal mode problem, but there is evidence that this path integral understood in the saddle point method, including loops, is a sensible method. And it's not only and I should say another thing that ADS-CFT has given us. So another question that one could ask is, what if you have multiple saddles? Yeah? it could be that the equations have multiple solutions, and then it becomes a more subtle question of which of these saddles contribute. Should we sum over all of them? Should we sum over some of them? And what is the principle to select which saddles we should consider? There is at least a few examples in ADS-CFD, one known as the Hawking-Page transition example, where there are two saddles that contribute to this path integral, given boundary conditions. And so there is evidence that multiple saddles may well contribute. And so we should take seriously the idea of exploring the space of saddles beyond perhaps what we think is the most intuitive or physically motivated one, because they may contribute. Yeah.
Thank you.
Yeah. Okay. So, yeah. So I think this is where I wanted to go with the development of a more sort of global perspective of this cosmologies and the quantum features. And, you know, I'm now going to return back to sort of Earth, which is that even if this picture is true, even if we could solve this picture, we ought not to forget that if we are in a cosmological scenario where space is expanding relentlessly, yeah? Which slide should I choose? Let's this one. Even, you know, we should remember that there was this simple condition that in the presence of accelerated expansion, space can expand so fast that any creature measuring things quasi-locally, and quasi-locally just means scales that are much larger than the Planck scale, but much smaller than the size of the universe, if you want a formal definition. So, for example, 100 kilometers. Even if this very global picture is true, we still have to confront the fact that our world is not, at least the world that we can experience, is not the whole global Cauchy surface that DeWitt hypothesized. And there's a few ways out of this, and this is another question of whether we should formulate the problem from the point of view of the experience of someone observing cosmological information and trying to deduce features, right? So what are we doing? Cosmology, we collect redshift patterns in different directions, light, radiation, whatever, and then we start to reconstruct, based on this data set, the large-scale structure of the world. But at the same time, there are portions of the world that if the world continues to expand, remember, what was the condition? Something like this. That the size of the horizon, T now, was this quantity over here. So this is the size of the horizon, of the cosmological horizon, multiplied by scale factor to get sort of proper size. If we are in a world that expands relentlessly and shields us from other portions, yeah, to what degree can we meaningfully extract from this very, very, very global bird's eye view of the universe physical predictions about the portion of space time that we can actually experience, yeah? So this is an important question, that even if someone handed you, let me rephrase it more prosaically, if someone handed you the wave function of the universe, here, let's put it out of the hand, here you go, this is it. What would you do with it? And this is not it's a serious scientific question. It's, you know, if I was studying the energy levels of a hydrogen atom or transition, I would know what to do with it. But if someone handed me the full, complete wave function of the universe, to go from that to say, let me now predict today how many galaxies there are in a volume of, you know, 100 million light years, you know, it's actually rather subtle. So, and another point, which is a little more formal to make, is that whenever we treat physical problems in gravity in the context of black holes, yeah, so let me invoke black holes for a moment. Whenever we think about black holes, so let me remind you what sort of the canonical Penrose diagram of a black hole looks like, right? There's this horizon, yeah? Whenever we try to think about black holes and we start to ask questions that cut through horizons and start to require us to specify physics, you know, our theoretical framework becomes a little more troublesome, yeah? So, because there could be ambiguities or questions about the nature of the state in the interior of the horizon that we don't actually have access to, and it's not clear that we need to have access to. And there is a sense in which, for the black hole problem, perhaps it's best to try to focus on something like a mixed state or a density matrix that is codifying the physics inside this region over here, yeah? And so now, in the best case scenario, there may be a pure state that purifies this density matrix, and we can discuss it. But certainly, it's of interest to think about the problem from the point of view of a density matrix as well, and in a sense, perhaps more honest. Yeah? Similarly, in cosmology, perhaps we should also pause for a moment and think about whether there's a mixed state perspective that we ought to supplement or complement this more global perspective with respect to, yeah? And so this is generally a very hard question. So what would this even mean? Well, in its most formal sense, you could imagine something like taking your pure state, whatever your cosmological pure state is, you could imagine now considering this thing on some slice, and even defining this slice is a bit of a gauge-dependent thing. Let's say you fixed it somehow by declaring that it's the slice where the temperature of the universe is uniform or with some physical relational quantity. Path integrating over all configurations outside of this slice, yeah, and obtaining a density matrix out of this object, yeah, some density matrix that depends only on the configurations in the interior. Okay, so H in, this would be, the output of this thing would be some H in, so the indices of the density matrix would be H in Ij, H tilde in Ij, yes, and density matrix. Remember, just like in quantum mechanics we have psi of x, here we have psi of h, so density matrix, yeah. And, you know, so one formal way to do that is this over here. Now, this is a subtle problem because there's a lot of challenges with cutting a local quantum field theory in constant regions. The Hilbert space of a quantum field theory doesn't truly factorize locally. There's going to be divergences, ultraviolet divergences, associated to this operation, in addition to gauge ambiguities of specifying the slice or the location where you cut off. And so you see quite quickly that this over here is actually a rather subtle task. Yeah? Even just defining the setup of the problem. How do I define where I cut off? The metric is fluctuating. What is the location of the surface? Should I tolerate an error? Yeah? How do I deal with the fact that the Hilbert space doesn't factorize? This is going to invariantly give rise to ultraviolet divergences, as these kind of calculations often do in quantum field theory. And so it's an interesting question to ask. And this is a problem that people are trying to address in more recent literature. A revisiting of the old problem of the local observer, let me give you some literature on this. 1109, 4942, and more recently, in the language of algebraic QFT, 2206, 10780. And so that's sort of examples of this type of literature. And just, I won't have time to discuss this probably, but just for the sake of completeness, there's another perspective that is stemming in the literature, whereas an auxiliary device, so this is just an aside, people are trying to see whether they can define a more local perspective cosmology by excising a time-like, finite-sized time-like tube from a 4-manifold, from the space-time manifold, and trying to see whether this, at least as an auxiliary device, but also maybe more seriously, it could constitute a way to formulate a more quasi-local perspective of the problem. Okay, so let me just mention that because it's sort of it's a complementary literature for those of you who want to. So you see now we're reaching topics that are more recent. Okay, so I'm happy to talk about this offline, but I can't talk, I would need more hours to talk about everything I'd like to talk about. But let me try to find, in the spirit of sort of having a concrete theoretical problem at hand, let me try to find a version of this scenario, this setup, this density matrix, that we can be as crisp as possible, okay? Given the motivation of the setup, I think it's important to find examples where we can study such objects, properties of these density matrices, to the sharpest extent possible. And for that, I'm going to return now to of course. I'm going to return now to our de Sitter geometry and motivate a setup for this kind of problem, which has to do with what I called the static patch portion of de Sitter. And let me remind you of the geometry in the next 5 minutes, and then we'll delve into the wild world of the static patch in the next 2.5 hours. So remember the Penrose diagram. Yeah, of de Sitter. And remember this observation we made, that this is an example of a space that has these cosmological horizons. So if you happen to be in this simplified world, one of these observers in a pure de Sitter world, yeah, and here you are sitting with your little laboratory, yeah, making your measurements, you know, physics over here is just out of causal contact, yeah, and so you could imagine a situation where you would like the physics of the static patch alone, okay? And so you'd like to trace out somehow the Hilbert space of fields or states outside of your static patch. Now, this is still, this problem at the level of QFT in a fixed background is approximately sensible, except for the fact that we have to cut our Cauchy slice at a point, which is not something quantum field theory generally enjoys. It yields infinities because of the ultraviolet sensitivity of the very local nature of the cut. However, you could try to regularize that somehow. And in the context of gravity, this becomes a little more subtle because we have no diffeomorphism invariant definition of where the location of the surface is that we're wishing to cut. However, by good fortune, much like for the case of black holes, it turns out that the Euclidean version of this problem happens to be rather reasonably well defined for the gravitational case as well. And so what I'd like to do now is discuss first in a simple QFT setting, and then we'll go to gravity, what it might mean to study this static patch portion of de Sitter. What theoretical quantities, what calculable quantities are associated to this object rho? Okay, so that's where we're heading now. Okay, so we're going from the very global to the quasi-local, and we're going to see if we can build some computational framework to think about the features of rho. Yeah? For instance, a very basic feature would be how much quantum information is coded in rho, which is what the von Neumann entropy of entanglement would be computing. So that would be a quantity that codes how much quantum information and how that quantum information, and this ties to a question that was asked a few days ago, and how that information is coded in rho. So for instance, if you have a quantum field in this representation or that representation, you know, things like that. Okay, so we'll get a bit of a flavor in that, and then we'll see how far we can go with gravity and what it encompasses. Okay, so now we pause it here, and then we'll continue afterwards.
I have three questions. It's clear to me that the minus sign that you have there for the conformal mode problem is the same minus sign that you have been explaining here. But is the conformal mode problem the same problem that you had with the wild transformation when you did the large volume? Or those?
Well, you see, because it's in Euclidean, and when you have positive curvature, it's very difficult to have large volume.
Right.
I don't have access to that regime. There's theorems that, at least for saddles with positive curvature, always force them to be rather compact. Yeah? And so it shields itself from that regime. Yeah.
And in those technical difficulties that you showed for the inner product, does that improve if you have like mini superspace models or some kind of restriction like that?
Mini superspace can guide some intuition as to the properties of this thing, but it's a very tricky thing to do because we're truncating pieces of the metric in no systematically controllable way. So I'm very cautious about the lessons of mini superspace. We have to treat it as a broad guide, but not a technical guide. So mini superspace, as far as we know, this is an off-shell thing. We have to do the patterning over all metric configurations, and we restrict to some without any other argument. I don't think that can constitute an answer. Yeah.
And the last one, you said from ADS-CFT, we know that the Euclidean path integral is well defined in some sense. How do you link that with the discussion that you mentioned about the lapse that is only positive, and then you are not, you don't have like the delta function representation?
Yeah, so, well, there's one more essential difference in ADS-CFT, that the space has a boundary. And so there's this more natural quantity, which is the boundary Hamiltonian, and we typically define things with respect to boundary quantities. So there's a sense in which ADS-CFT avoids a very detailed Wheeler-DeWitt treatment, although there are at least perturbative Wheeler-DeWitt treatments in ADS-CFT. But when you're in this perturbative regime, you don't need to confront these issues as dramatically. And in fact, there's a very natural, you see, enforcing the boundary condition of ADS at infinity restricts actually quite significantly how far you can go away from the perturbative regime, and it almost protects N from going too far away from these regions. And there's a very nice gauge that you can fix called the York gauge, where the trace of the extrinsic curvature along the slice is fixed, where you can, quite systematically treat this Wheeler-DeWitt problem ADS very nicely. And so I think ADS, in having a boundary, affects some of the more general problems of Wheeler-DeWitt. Much like in cosmology, if you're in this large volume regime, you're sort of conditioning away from the more general negative probabilities. Yeah. And so that's why it's an interesting question of now if the manifold happens to have boundaries more generally, how does this affect some of the issues that appear in Wheeler-DeWitt? So there's all sorts of interesting questions that may be sensitive to these features.
Thank you.
Yeah.
We have two. The first one is that you said that even if someone gives you the wave function of the universe, you should trace out the configurations of metrics that are outside of your causal region. But how do you define that that out? If you
That's right. So that's already, but you start to see quickly the challenges with. It's a challenge. Yeah, I didn't give you the answer. I gave you the question. Yeah.
And the second one is if whether we can ask this reduced state what time is.
Well, maybe relative to something else, but a priori, again, in gravity, there's no intrinsic time. That's why I was saying that maybe if you have some other quantity, like the average temperature of the world, or you still have to confront that issue. Yeah.
Okay, thank you.
Okay, no more questions.